Good afternoon to all. So today we are going to learn the chapter number 5, that is Z transform. Okay. So basically Z transform is nothing but we are going to have a frequency response of a signal in Z plane. Okay. So we are using different methods of transform, that is continuous time Fourier transform, discrete time Fourier transform. Why we are using these methods? Okay. The answer is to get the frequency domain of the signal. Okay, for example, if you are going to analyze a system which is continuous time, okay, CT, then you have to go with the continuous time Fourier transform, also Laplace transform. Okay, if you are going to analyze a system which is of discrete time, that is DT, digital signal, then you have to go with the discrete time Fourier transform, as we have seen earlier in the chapter number 4, and also you are going to go with the Z transform. So for discrete time signals, for approximation and analysis of discrete time signal, we can use DTFT as well as Z transform. Already we have seen the DTFT, properties of DTFT and numericals solved. Okay. So there are some disadvantages or limitations of this DTFT. So that is the reason why we are using the Z transform. Okay, so in concluding, we can say that I'll zoom it. So in concluding, for approximation of linear time invariant system, we need to deal with the Fourier transform. Okay, so now this chapter consists of Z transform. It is used to analyze the discrete time LTI system. We already know that Fourier analysis of continuous time signal plays a major role in frequency domain analysis and design of continuous time signals and system. So another powerful tool for analysis and design of continuous time signal and system is the Laplace transform. Okay, so Laplace transform covers broader class of continuous time signals. So now our interest lies in frequency domain analysis and design of discrete time signals and systems. So the Z transform provides a valuable technique for frequency domain analysis of discrete time signals and design of discrete time LTI systems. Furthermore, Z transform offers extremely convenient and compact way to describe digital signals and processors. So this chapter we are going to develop Z transform and discussing the various properties of Z transform. So the Z transform of a discrete time system is given as the formula is written here. Okay, this is the formula which states that Z transform Z dot T means the Z transform of x of n equals to x of z. Okay, so whenever we are going to take the Z transform of x of n, we are going to have x of z as an output. So input is x of n, output is x of z. So this is a simple x z transform formula. So now inverse Z transform will be, we have already given x of z and we have to find out x of n. Okay, we will see it further. So the formula for x of z, simplified formula is x of z equals to summation of, okay, summation of n equals to minus infinity to plus infinity x of n into z to the power minus n. This looks similar to discrete time Fourier transform. Only the difference is there is missing, okay, e to the power j minus j omega n. Okay, that is the only thing which is missing. So where z, this capital Z is complex variable. Okay, so z is nothing but r into e to the power j omega. As I already said, it looks like discrete time Fourier transform because the term missing is only e to the power j omega. So now we can denote this z as r into e to the power j omega. Okay, where r is the radius of circle. Okay, so z transform converts differential equations into algebraic equations. Okay, therefore it simplifies the analysis of linear time invariant discrete time system. So keep in mind, whenever we are going to approximate LTI systems which are discrete time, we have to use Fourier transform or Z transform. Z transform is a more convenient way and a more reliable way, okay, because it has more bandwidth of spectrum. And also for LTI CT system, means continuous time LTI systems, we are opting for continuous time Fourier transform or Laplace transform. Okay, so Z transform is nothing but counterpart of Laplace transform. So the formula for inverse Z transform is, so I have given here Z inverse x of z. Okay, means inverse Z transform of x of z is x of n. As I already said, in case of inverse Z transform, they have given x of z and we have to find out x of n. Okay, so now x of n formula is 1 upon 2 pi j. Okay, closed integration. This is closed integration of x of z, already given in the numerical, and z of to the power n minus 1 dz. Okay, this is the formula for inverse Z transform. We are going to solve numericals based on Z transform and some numerical based on inverse Z transform, and then we are going to have a look on different properties of Z transform. Okay, in this chapter. So first of all, as I said earlier, Z transform and discrete time Fourier transform, it has a relation. Okay, they are quite similar to each of them, so it has a relation. So relation between Z transform and discrete time Fourier transform is, okay, so this is basically a small derivation, I'll explain. So Z transform of a discrete time signal is defined as, we already know the Z transform. Okay, this is the Z transform. X of z equals to summation of n equals to minus infinity to plus infinity x of n to the power x of n into z to the power minus n. Put this as equation number 1. So we know that already z is nothing but, okay, complex variable. We can denote z as r into e to the power j omega. So put this value of z, in this equation number 1. Okay, so then just put the z equals to r into e to the power j omega. So this z will become r into e to the power j omega. Then this z will become r into e to the power j omega to the power minus n. Okay, so now just split the powers. Okay, this r will multiply to this r will be multiplied to this minus n. Okay, so r to the power minus n, this e to the power j omega will be multiplied to the minus n. Okay, so this will be e to the power minus j omega n. Okay, so now if the radius of, we know that r means radius of circle. Okay, so if r is equals to 1, then what happen, then this will become 1, so only this term will remain. So x of e to the power j omega equals to summation of n equals to minus infinity plus infinity as it is, x of n as it is. So now this will become 1 and this will remain. Okay, this term remains. Put this as equation number 2. So from combining both the equations, we can see that x of e to the power j omega, this one, okay, is equals to this. Okay, x of e to the power j omega means equation number 1 and equation number 2 are the same when r equals to 1. Okay, equation number 2 is this one, and equation number 1 is this one. Only the difference is we have to put e to the power j omega here. Okay, so I have written already. So from 1 and 2, x of e to the power j omega equals to x of z. Okay, so this is discrete time Fourier transform, this is z transform. These are equal when, this is the condition, when z equals to r into e to the power j omega. Okay, and r equals to 1. Okay, so the discrete time Fourier transform and z transform are equal only and only when this z and r equals to 1. Okay, so from equation number 2, the right hand side means this right hand side is the Fourier transform of x of n. Okay, we already know that. So we can conclude that the Fourier transform of x of n is same as the z transform of x of n. Okay, so this Fourier transform of x of n already we can conclude because of this equation. Okay, because of this formula, x of n evaluated along the unit circle centered at the origin of the z plane. Okay, so now there is a basic term which is called as region of convergence, ROC. Okay, you might have learned it in the M3 Mathematics 3. So after finding out the z transform, we are going to find out the region of convergence of that particular, okay, x of n. So it is placed in the z plane already. Okay, z plane has imaginary values and complex values. Okay, sorry, real values and complex values. Real values on the x-axis, complex values on the y-axis, and we have to plot the poles, and according to that we have to draw the region of convergence. Okay, so now applications of the part related to ROC we will see in the next lecture. Okay, it's a quite complex part for to understand, but very simple. So applications of z transform. Okay, the main thing, first of all, it is used for analyzing LTI discrete time systems. Okay, already we have seen analysis and approximation of linear time invariant discrete time systems. Also pole zero description of discrete time systems. As I said earlier, the term ROC we require in Z transform to plot the convergence of the x of n. So it plots the pole zeros. Okay, the frequency response estimation, we can estimate the frequency response of x of n by using Z transform. So it is widely used in the field of digital signal processing. So maybe in the next semester or in the last year, you are going to learn the digital signal processing, okay, or image processing, these kind of subjects. Z transform is very essential, okay, in that filter design, okay, and to solve the difference equations. Already said that the Z transform converts the difference equation into algebraic equations. For solving the difference equations, Z transform is used. Okay, so now we are going to see, although we have discrete time Fourier transform, then why we are opting Z transform? Why there is need to go to Z transform? Okay, we will see that in the part of existence of DTFT. This is a very important concept regarding the examinations. Okay, existence of DTFT. So now the Fourier transform exists for a discrete time sequence x of n if and only if the sequence is absolutely summable. Okay, means this summation of x of n should be finite. Okay, it should not be infinite. That is, the sequence has to satisfy the condition. This is the condition. So the condition is nothing but summation of n equals to minus infinity to plus infinity. Okay, mod of x of n is less than infinity, means this condition says that x of the summation of x of n should be less than infinity. Okay, or the sequence should be summable. If it is not, if it is infinity, it is not summable. If it is less than infinity or finite, it is called as summable. So if this condition is satisfied by the DTFT, then only DTFT exists, otherwise DTFT not exist. So now the DTFT does not exist for sequences that are growing exponentially. Okay, this is the main, this is the important point, which states that the DTFT for the sequences that are growing exponentially. Okay, exponentially growing means, okay, there are two terms: exponentially growing, exponentially decaying. Okay, exponentially growing means it is growing continuously. Okay, it's not decaying. For example, signals are a to the power n u of n. Okay, a greater than 1, so it will go to infinity. It will not be finite since they are not absolutely summable. These kind of sequences are not summable. That is the reason why the DTFT will not exist for this kind of sequences. So therefore DTFT method of analyzing a system can be applied for a limited class of signals. Okay, so we can apply the DTFT, or we can find out the DTFT of a signal for only limited class of signals. There is a limitation in the types of signals, variations of signals, and type and class of signals. Okay, for each and every class we cannot find out the DTFT. So moreover, this method can be applied only to asymptotically stable systems, and it cannot be applied to unstable systems. Okay, so earlier they said that it is applicable for only limited class of signals. Okay, it cannot be applied to unstable systems. It is applicable only to asymptotically stable systems. Okay, asymptotically stable systems means marginally stable systems, stable or marginary. Okay, there are three types. First one is stable, second one is unstable, third one is marginally stable. So the DTFT can be used only for the sequences whose system function h of z has poles inside the unit circle. Okay, this point you are going to get in the ROC concept. Okay, so it basically states that your system h of z, if it has poles inside the unit circle, then only the DTFT will exist. Okay, so now some basic problems on Z transform. Okay, so the problem is given as a finite sequence. Finite sequence, already we know that restrictions. Okay, no, not infinite. Finite sequence x of n is defined as, x of n is given as, okay, x of n first pi 3 minus 3 0 4 minus 2. We have to find out x of z. Okay, so this is a basic Fourier transform. Sorry, basic Z transform. You have given x of n, you have to find x of z. So we know the formula: Z transform of x of n equals to x of z. So whenever we are going to take the Z transform of this x of n, we are going to get x of z as an output. So formula of x of z, we know that summation of n equals to minus infinity to plus infinity, x of n to the into e to the power x of n into z to the power minus n. This is the basic standard formula. Just put down the values. So now while taking the summation, first of all see the sequence. Okay, 0 1 2 3 4 5. Okay, The sequence starts from, as there is no arrow given downside the number, so 0 will start from 5. Okay, x of 0 will start from here. We have seen in the convolution part. Okay, so 0, 1, 2, 3, 4, and this is 5. Summation will be from 0, n equals to 0 to n equal to 5. Okay, because of the sequence, length of the sequence. Summation is nothing but length of the sequence. It varies from minus infinity to plus infinity. And then x of n, z raised to power minus n as it is. So now we have to put the values of n from 0 to 5 in this. Okay, n, and here n. Okay, so put n from 0 to 5. So first one is 0. First value of n is 0. So then x of 0 into z of 0. Okay, then n equals to 1, x of 1 z inverse. Then n equals to 2, x of 2 z raised to minus 2. Then n equal to 3, x of 3 z raised to minus 3. Then x of 4 z raised to minus 4, and lastly x of 5 into z raised to minus 5. Okay, so the value of z to the power 0 is 1. Okay, as e to the power 0 is 1, z to the power 0 is always 1. So just put the values. So now x of 0 value is nothing but this 5. This is x of 0, this is x of 0, this is x of 1, x of 2, x of 3, x of 4, x of 5. Okay, just put the values. X of 0 5, z is to 0 1, this is 5 only. X of 1 is 3. Okay, here, and z inverse as it is, minus x of 2 is 3, x of 2 is minus 3, so minus 3. Okay, x of 4 is plus 4, x of 5 is minus 2, x of 4 is plus 4, x of 5 is minus 2. Okay, then the term with respect to it as it is, this is nothing but the z transform of this x of n. Okay, so in the next problem we will see the down arrow. Okay, in this problem is similar, just they have given the down arrow here. Okay, so sequence will start from the 1. Okay, so this is x of 0. I'll zoom it. This one is x of 0. Okay, and remaining, this is x of 1, x of 2, this is x of minus 1, x of minus 2, x of minus 3. Okay, then just same procedure, write down the formula for z transform. This is the formula for z transform. Okay, then we have to put the summation according to our sequence. Our sequence starts from x of minus 3, ends to x of minus 2. So summation will be from minus 3 to plus 2. Okay, so now just put the values. N equals to minus 3 to plus 2, x of n z to the power minus n. So this is equals to, so now first put n equals to minus 3, then minus 2, minus 1, 0, 1, 2. Okay, 5 values. So while putting n equals to minus 3, this n will become minus 3, and this n will become plus 3, because minus n, when we put minus 3 as n, then it will be minus, in bracket minus 3, it will become plus 3. Okay, so again same, minus 2, this will be z square, minus 1 z to the power 1, then x of 0 z to the power 0, x of 1 z to the power 1, x of 2 z to the power 2. Just put the values of this sequence. X of minus 3 is 5, x of minus 2 is 3. Okay, x of minus 3 is 5, z to the power 3 as it is. X of minus 2 is 3, then z to the power 2 as it is. X of minus 1 is 1, z to the power 1 is, x of minus 1 is 0. Okay, and z to the power 1 is whatever the value is, 0 into some value is 0. Okay, so this term will be 0. Then x of 0 is 1, then z of power 0 is 1. Okay, 1 into 1 1, then x of 1 is 2, z to the power minus 1 as it is. Here is it is minus 1. Okay, corrected. Then the x of 2 is 4, and z to the power minus 2 as it is. So this is the z transform of this x of n for the for this kind of sequences. Okay, so this is the answer. And today we have seen introduction to z transform, relation between z transform and discrete time Fourier transform, and some basic problems on z transform. So in the next lecture we are going to start with the complex problems on z transform, which includes the region of convergence. Okay, so till then, say goodbye. uh, and I hope you are all are safe and have a great day. Okay, okay.